In section 5.2, we're going to be extending our discussions from what we did in the previous section, but now to just generalized normal distributions. If you remember, in section 5.1, we primarily focused on the standard normal distribution. That is the one that goes with z-score. So if you hear either the buzzword standard normal distribution, or if you see them using a z-score, that's referring to the standard normal, and that is the special normal distribution whose mean is equal to 0 and whose standard deviation is equal to 1. If we look at a lot of the other normal distributions that are out there, things like human IQs, weights, ages, birth weights, etc., they will also tend to be normally distributed, but they will have different values for their mean and standard deviation. One of the things we made a point of emphasis on earlier in section 5.1 is that, again, it's two values that determine the shape overall and the way that a normal distribution works, and that's the mean and the standard deviation. Let's take a look at example 1. In this setup, they tell us that IQs are normally distributed with a mean of 100 and a standard deviation of 16. Okay. They ask us to find the percentage of people with IQs greater than 115. So especially in problems like this, whenever you see them kind of write down or describe the information to you, it's a good idea somewhere off to the side, highlight that information. What is the mean? What is the standard deviation? For this problem, the mean is 100, standard deviation is 16, and as we preached in that last section, try to draw the shape of that normal distribution. We know it's going to be a bell-shaped curve, and here the mean is going to be 100, so that's where the peak of the curve would appear at. We want to find the percentage of people with an IQ greater than 115. Now that's a value that's going to be larger than the mean, so 115 would be somewhere over here, and we know that greater means go to the right as it would pertain to a number line. So we're looking for that percentage, which would going to be the same thing as the proportion, which would be this probability, but just changed to a percentage at the end. We know that that probability, or that proportion, is equivalent to the area under the curve. So once again, we're going to need to use that normal CDF command. I pull up my calculator. I go to second distribution. Option 2 is normal CDF. Again, having that region, when you sketch that region, that really gives you a head start in terms of defining the lower and upper limits for the region. Here the region extends as far to the left as 115, so that's our lower bound. It goes all the way to the right, like towards positive infinity. For us, we're using as a fill-in that 1 second comma E99. Now, this is not a standard normal, this is not a z-score anymore. We have to be very careful. The mean for this distribution is 100, and the standard deviation was 16. Once we have everything set up, we're going to go ahead and hit paste, and then hit enter. Again, for those of you using the TI-83, you will not see this previous screen that I just saw, that normal CDF. When you hit normal CDF on a TI-83, that'll put that command on your home screen. And it's kind of up to you to have to remember the order in which those four inputs go. It goes lower bound, then comma, upper bound, comma, mean, comma, standard deviation. So lower, upper, mean, standard deviation. Go ahead and hit enter, and we get a probability or a proportion of 0.1743. 0.1743. Now, they specifically asked in this question to find the percentage. All we need to do is change that decimal to a percent by sliding the decimal spot 2 places to the right. So we would say that 17.43% of those individuals would have an IQ that is greater than 115. Let's take a look at the next one. In example 2, they tell us that the lengths of Atlantic croaker fish are normally distributed with a mean of 10 inches and a standard deviation of 2. We're going to randomly select one of these types of fish, and in part A it says find the probability that the length of the fish is less than 7 inches. So this time we're looking for a probability. Again, it's a good idea to go ahead and first do a sketch of this graph. This distribution has a mean of 10 and a standard deviation of 2, so I can just kind of go ahead and draw my bell-shaped curve here. The mean would be 10. If I want to find the probability that a fish has a length of less than 7 inches, 7 is less than 10, so that would be somewhere to the left of the mean. And then we're looking for the probability that it's less than that, so we would shade everything to the left like this. We know that that probability is equivalent to this area under the curve, and we can find that using the TI calculator. Second distribution, go down to normal CDF. If you're curious what the CDF stands for, it actually stands for cumulative density function. This region goes all the way to the left. That's going to be -1, comma E99. The upper bound of that region, the shaded region, goes as far as 7. And now we need the mean and the standard deviation. The mean was 10 for the fish, and a standard deviation of 2. Go ahead, paste it, get it to the home screen, and hit enter. And we would get to 4 decimal places, 0.0668. So the probability that one of those fish chosen at random is less than 7 inches would be about 0.0668. Not an unusual event, but not a very likely event either. If we wanted to give an interpretation, most people kind of interpret and understand percentages better than what they do probabilities. We could turn this proportion into a percentage by just moving the decimal spot 2 places to the right again. So the interpretation would be that about 6.68% of all of these types of fish would be less than 7 inches in length. Let's take a look at a follow-up question. Find the probability that the length of the fish is between 7 and 15. So again, go back. You probably want to do a new sketch for this. We have a mean of 10. 7 is to the left of the mean. 15 would be to the right. And we want the probability that the length of the fish is between those two values. So for this example, you'd be shading everything between 7 and 15. We can find that answer by going to our second distribution, normal CDF. For this particular problem, the left bound would be 7. The right bound would be 15. That's the upper bound. Still a mean of 10, standard deviation of 2. Go ahead and hit enter. And we would get a probability of about 0.9270. This 8 would bump that 9 up to a 10, which would carry over and bump that 6 up to a 7. So 0.9270. The interpretations, we could say that, move it over 2 places to the right, 92.7% of all Atlantic croaker fish would be between 7 and 15 inches in length. For part C, they ask us to find the probability that the length of the fish is more than 15 inches. So we want more than 15. So we'll be looking for the area to the right of 15 if we draw it and sketch it out. You can be a little bit industrious. If you look at the previous work that we did for this problem, we've already found the probability that it was less than 10, the probability that it was between 7 and 15. One way you could find the probability that it's more than 15 is if you did 1 minus these two areas combined. That would also give us the area that it's above 15. Or we could just do it as one simple calculation using our normal CDF. For this particular region right here, more than 15 would mean this region above. That'd be second distribution, normal CDF. The lower bound of this region is 15. The upper bound would be like positive infinity, so we're going to use the 1, second comma E, 99. Mean of 10, standard deviation of 2. Go ahead and hit enter, and then enter again. And we would get a probability of 0.0062. 0.0062. So 0.62% of all Atlantic croaker fish would be more than 15 inches. Let's take a look at example 3. They say that a survey indicates that for each trip to the store, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes. Find the lengths of time spent in the stores are normally distributed and represented by the variable x. So we have a distribution here that's its normal distribution. The mean is 45, the standard deviation is 12, and we want to find the probability that somebody spends between 24 and 54 minutes in the store. If you want to, you can go ahead and sketch that out. To compute that probability, we're going to do second distribution, normal CDF. Between 24 and 54 means 24 will be the lower bound, 54 will be the upper bound. For this setup, the mean was 45 and the standard deviation was 12. Get everything plugged in, go ahead and hit enter, and we would get a probability of 0.7333. As a percentage, that means that 73.33% of all shoppers would spend between 24 and 54 minutes in that store. If we had, let's say, 200 shoppers, and they wanted to ask how many of them would spend between 24 and 54 minutes in the store, then that's kind of like a percent of style problem from like basic math. We already know that it's going to be about 73.33%, or a probability or proportion of 0.7333. So it'd be 0.7333 of those 200 shoppers. You would just need to multiply. So 0.7333 times 200 would tell us that approximately about 146.6, probably would make sense to round it up, about 147 of those 200 shoppers would spend between 24 and 54 minutes in the store. So again, it's always important to pay attention to the directions of a problem. Sometimes they might ask for probability, they might ask it as an area question. We know those two things are equivalent. Other times they might ask for a percentage style response, or even something like part B here of example 3. They're not looking for a specific probability or percentage. They actually want to know a specific number. Okay, so it's a percent of style question in part B. Let's go back and finish the other remaining part of this one. What's the probability that a shopper spends more than 39 minutes in the store? So for more than 39, again, if you want to, you could go ahead and sketch it out. Second distribution, normal CDF. If it's more than 39, that means that it would be to the right or above 39, meaning 39 would be the lower bound. The upper bound would be positive infinity, so 1 E99. Mean of 45, standard deviation of 12. Go ahead and hit enter, and we would get to 4 decimal places, 0.6915. 0.6915. We have one more example in 5.2. Let's take a look at math SAT scores. They tell us that the SAT math scores are normally distributed with a mean of 515 and a standard deviation of 116. What percentage of SAT scores would be less than 500? So again, we're looking for a percentage this time. Let's find the proportion of the probability first. If it helps, go ahead and sketch it out. Here's our bell-shaped curve. The mean is 515, which would be right here. We want to know the amount or the percentage that's less than 500. 500 is to the left of the mean, and less than it would be everything to its left. So we need to first find this probability proportion here. We can do second distribution, normal CDF. It goes all the way to the left, so the lower bound would be negative infinity, negative 1 E99. The upper bound would be 500. For this data set, the mean was 515 with the average math SAT score with a standard deviation of 116. You can go ahead and hit paste and hit enter. And that would tell us that the probability, the proportion of individuals who scored less than a 500 would be about 0.4486. Because they wanted it as a percentage, just change that decimal to a percent, slide the decimal spot 2 places to the right. So 44.86% of the SAT math scores would be less than 500. In the last part, they say that if 1,500 SAT math scores are randomly selected, how many of them would we expect to be greater than 600? So what we're looking for this time is an actual number, a number of these test scores that we would expect to be greater than 600. Well, we can find the proportion of them that would be greater than 600. 600 is more than the mean, and greater than would be go to the right. So I can do second distribution, normal CDF. The lower bound of this region would be 600. The upper bound would be 1E99, because it goes all the way to the right. Mean of 515, standard deviation of 116. Go ahead and hit enter. And we would get a proportion of about 0.2319. So 0.2319 of all of these SAT scores for math, we would expect to be greater than 600. Well, if we have 1,500 of these scores, then it's 0.2319 of them, so times the 1,500, would tell us how many we would expect to be greater than the 600. If we go ahead and multiply, it's going to be approximately rounding to the nearest whole value. It's going to be about 348 of those tests. So of our 1,500 selected, we would expect 348 of them would have a score greater than 600.